Okay, see. Laws of motion, okay, very important topic for entire class 11, of course, and class 12 also, okay. Without this topic, okay, you cannot go further in this year, okay. You will need it in next chapter, then actually most of the chapters will be needing a concept about force. Okay, that's what we are going to do right now, okay. You already have some idea about laws of motion. You started in class 9. Okay, we will be talking about that, but we'll be talking in details today, okay. Moreover, I told you last time also, I don't know, I told you this batch or other batch, okay. You'll be needing this in your next life also, so study this life properly, no, to save time. Okay. So yeah, so we'll start. Okay, see. Let me check what I need to teach you so that I go in order, no. Okay, let's start. Let's start with force. Start speaking, guys. Start speaking. Anything that you know about force. Start. Wait. Okay, last time also I scolded last batch. Okay, because my students, I noticed this class 12 also and this batch class 11 also, they don't never ask me questions. So that is bad. Okay, you are science students.
Okay, sir.
Okay means no. Okay means you have to ask questions. No, you need to have. You will have doubts. You need to clear your doubts. You're going to ask me whenever needed and all. Okay. Okay. I'll say. See, tell me. Start talking about force. Oi.
Product of mass and acceleration.
No. Push or pull. Right? We call it force. Can we measure it? Yes, we measure it in a units called newtons. Does it have direction? Yes. So it's a vector quantity. Yes or no? It's a vector quantity. What is the direction of force? That let's be clear with direction of force. How do we know direction of force? Tell me some formulas that you know about force first. F equals to mass into acceleration. Okay, fine. You know about this. Okay. Tell me about direction of force. It's there in the board only, the answer. The direction of acceleration, right, gives you direction of what? Force. There's another way to express this law. Okay, you have learned in class 9, no? Rate of change of momentum. The change of momentum, the direction in which the change of momentum takes place. Okay, that's the direction of force. It's a vector quantity. We'll have to keep on talking about direction. Okay. Since it's a vector quantity, we will apply all the rules, okay, of vector addition. Yes or no? If I have force F1 and force what? F2 incline at an angle of what? Theta with each other, you know how to add them. Okay. You've also seen force being multiplied with displacement, right, in dot product. Yes or no? F dot S, that will give you work or force? Work. F dot S will give you work. Okay. So you know how does force work, okay? Okay. Tell me about effects of force. What can force do? We have not reached till here. We will again discuss this topic properly. Don't worry about that. Okay. Please tell me first effects of force. What can force do to us? Change.
Change position.
Change position. Force. No.
Change the rate of speed.
Change the rate of speed. Okay. That means change, or let's say change what? Change speed. That means it can make a body move faster or it can make a body move slower. Force can do that, okay? Without force, a body can never become slower. Without force, a body cannot become faster. Okay. Anything else? Hint. Yeah. A force can change the shape. Obviously, you know about this, okay? Come and apply force, we can change the shape, okay? But in this entire topic, okay, we will be talking about rigid bodies. See, rigid bodies. What are rigid bodies? Bodies, even if you apply what? Force, shape is not going to change. They're solid bodies, very hard bodies. Rigid bodies are very hard bodies, okay? So when you apply force, right, it can only come and change what? Speed. All the force will be used to change what? Speed, and the shape of the body will not change. Means none of the part of the force, okay? Not even a small amount of force will be used to what? Change the shape of the body. Can you understand? Okay. Anything else you want to talk about force before we proceed? Tell me. No, nothing. You don't want to say anything, no? Okay, let's proceed. Okay. After this, okay. If it stops, you tell me, huh? It stopped or what?
No, sir.
No. Okay, fine. Then see, okay. There was a person, okay. There was a person. His name is Aristotle. See, I'll not tell you the year right now. Not Aristotle. Very old person. Okay. Olden times. Okay. He said this. He thought that if there's a body, right, and it's moving with a velocity, let's say what? V. The problem with him was he thought that we need force to maintain this motion. Can you understand? It's going to keep on moving with what velocity? V. Not going to change the what? Velocity. He thought that we need what? Force. Okay, Newton comes and says that this idea is wrong. Can you get my point? According to Newton, this idea is wrong. We don't need force to maintain a velocity. We need a force to what? Increase the velocity or decrease the velocity. Can you understand? I'm repeating again. Okay, why do we need force according to Newton? To increase the speed or decrease the speed, or let's say to change the velocity, or let's say to change the direction also we need force. Okay, but for a body to just keep on moving with what velocity? Constant what? Velocity. According to Newton, it needs force or doesn't need force? It does not need force. I hope so you are clear with this idea. Okay, now see. Okay, so that was whose problem? And so we call this Aristotle's fallacy. Okay, fallacy means maybe something wrong he did. Okay, but later Newton comes in. Now Newton is going to put all the rules, and he's going to really put with formulas. Okay, so that's why it becomes very nice. Newton's laws. When I say Newton's laws of motion, right? What do you understand? When I say Newton's laws of motion, laws means what? Rules. Whenever motion takes place, it has to obey some what? Rules, no? So Newton is going to talk about that. Okay, you have already some idea about this. Okay. First one is called what law? First law. Second one is called second law. Third one is called. Very good. Very good. Okay. I have to ask you easy questions because difficult questions so you don't even understand. Okay. Okay. So first law, no? What is another name for first law? Law of inertia. This is also called law of inertia. So first of all, we need to study what is law of inertia, okay? Or what is inertia actually. If we understand inertia, no, we understand what is first law, okay? Second law, let me tell you right now only, is the most important law. And third law, already you know. Third law, every art student also they know. To every action, there is equivalent of, you ask them, they also know, okay? So science students, you guys know only, I think, right? Okay. So see, which is the most important one? Second, I'll tell you why. Because even if you don't write which law, first law, even if we don't talk about which law, second law contains both of them. Second law contains what law? Second law contains first law also, and second law contains third law also. There is a proof for this. We are going to do that also. Okay. So which is the most important law? Because it contains first law also indirectly it contains, and it also contains which law? Third law. Yeah, third law. Okay, okay. Now see, okay, let's talk about inertia. See, you have already heard about inertia. Let's talk about inertia properly. Okay, waiting. What is inertia? Tell me. Huh?
The tendency of a body to
Okay.
continue in a state of rest or motion.
Don't read from somewhere, huh?
Exactly.
No, no? Okay, good, good. Tendency of a what? Tendency of a body.
To continue.
Okay, to resist. Let's say to resist. To resist change in what? Change in the state of rest or of what? Uniform motion. This is called inertia. I know you have no idea right now what I'm saying. Okay, say. Let's take an example. Okay, suppose I tell you there's a box. Okay, its mass is how many kg? 1 kg. Okay, suppose there's another box. Okay, this is a bigger box. Its mass is how many kg? M2. Okay, this is M1, 1 kg. M2 is how many kg? 2 kg. Okay, if you ask the box, right, are you at rest? Let's say the box is saying what? I am at rest. Ask this bigger box also. What does the box say? I am also at rest. The smaller box also is at rest. Okay, you will agree with me that both of them will not move unless and until we apply a force, right? Okay, and that force has to be unbalanced force. What force? Because if I apply balance force, you understand balance force? I apply 10 newtons, 10 newtons. What will I call it? Balance force. If I apply 10 newtons, it is force or unbalanced force? Unbalanced force. Okay, so you need to apply what force? Okay, so let's apply really. Okay, let's apply a force called F. Let me apply same force to the bigger box also. Okay, you know what is the first box saying? The first box says like you say, I am a box. I have mass. I am 1 kg. I am at rest. I want to remain at. I don't want to move. What is the first box saying? I don't want to move. That means it is resisting. It is resisting what? Do you understand the meaning of resisting? No, resisting is opposing actually. Okay, so it doesn't want to move. Correct or not? Ask him again. What do you want to do? He says, I am at rest. I want to remain at rest. I think you got the idea, right? So he wants to move or doesn't want to move? Doesn't want to move. Unless and until you apply what? Force. Unbalanced force. Let's be clear. This is just not force. We call this unbalanced force. Let me be more accurate now. Okay, it is not just unbalanced force. It is net unbalanced force because you may have many forces acting on it. Okay, and you take the resultant of all the forces. Then you look at the body again. It's not just one force. Should be what force? Force or net force? Net force. Okay, you got some idea. Okay, so do you agree with me or not? The first body wants to move or says I don't want to move. I don't want to move. What does the second body says? I am also at rest. I also don't want to move unless and until I'm applied with what force? Unbalanced force. Okay, some net unbalanced force. You got the idea straight, right? It's correct, right? That's why we say that, okay, if you see this is happening with any body, right? These bodies will have to say indirectly or in short, he says, I have inertia of what? Inertia of rest. That's the meaning of having inertia of rest. Okay, look around you, any object, okay? Every object that you see, right, has inertia of rest. Look at the chair. You have seen a chair before also, of course, okay? But it has inertia of rest or not? It has inertia of, what does it mean? The chair is also saying the same thing, same dialogue. I am at rest, I want to remain at rest. You don't believe me? Look at the chair, it's not going to move. Are you clear? Yes or no? Okay. So this is the property with us or with everyone? With everyone. Everybody which has mass, be careful with this. Everybody which has what? Mass will have this property. Okay? No exception. Okay? Now say, if you ask this person, not for this person, sorry, this box again, no? Let's compare the box. You know what is saying? I am at rest. I will remain at rest more. I want to remain at rest more. I don't want to move, and I don't want to move compared more, okay? Compared to this 1 kg mass. Agree or not? Who doesn't want to move more? Tell me, 1 kg or 2 kg? 2 kg, right? Doesn't want to move more. If I push also, no? Who will resist more? 2 kg will say, I will not want to move. Compared to which kg? 1 kg. So who has more inertia of rest? 2 kg mass, right, has more inertia of rest. So if I ask you, okay, can we measure inertia? What is your answer? Yes. Just come and measure what? Mass. And you are going to measure inertia. Are you clear fully what is inertia? So if I say what is inertia of rest, it simply means what? The tendency of a body to resist. Resist the what? Change in the state of rest. He is resisting the change in the state of rest. He doesn't want to move. He's also resisting the change in the state of what? Rest. He also doesn't want to move. So both of them, they have inertia of rest. Who has more inertia of rest? 2 kg. Okay, clear. Very clear. Okay, I think it's clear, right? Okay, because of this, there are so many applications now. We have already done it. Okay, let's talk about that now. Okay, examples. I'm discussing right now inertia of rest. Okay, by the way, let me just quickly write what are the different types of inertia. Inertia of rest, inertia of motion, actually, okay, uniform motion, and then direction also, no? When they divide, you can divide like that, okay? So see, we'll discuss now examples of inertia of what? Rest, okay? Give me examples. Anything, which comes in. Huh? Chair, no, not chair, not chair. Some of the examples, practical examples, inertia of rest. Let me go back here, inertia of rest. Okay, you have seen this one. There is a what? Cup. Bucket also you can call it, no problem, okay? And you put a card on top of it, no? And put a coin here, no? On top of what? On top of the card, what do you put? Coin, okay? Looks like transparent card right now, okay? But no problem. You understand? What do? You come and flick it, no? You come and flick what? The coin or the card? When you flick the card, what does the card says before you flick it? I am at rest, I want to remain at. But look at this force. This force is directly going to hit this card and the card has to fly or not. Okay, after applying force, it has to move. No other option, okay? Yes or no? But what does the coin says? Coin says, I am at rest, I will experience force later. Not now. First, who will experience force? The card or the coin? So the card is going to fly, but he still wants to stay at rest. Yes or no? Okay. That's why even if the card flies, it has to fall. You can try this at home. Okay. Go home and try at night. Okay. No problem. Okay. Okay. I think you're clear, right? Okay. This is one example. Give me more examples quickly. Let's take a bus. Okay. This bus. Who's driving this bus? No. Bus. Bus is better. I saw one animation in YouTube. Okay. There was a lady here. Okay, sitting in a chair inside a bus. Chair also that one with the wheels. Okay. I will tell you how does the animation look like. It's very nice. Okay, right now the bus is at what? Rest. Okay, and the driver of the bus is also at rest. Everybody is at rest. This lady is also at rest. Okay, this lady right now, let me tell you again. It is standing. She is standing. Okay, to get the feel, no, let's make her stand. It's much better. She is going to fly. Okay, in front. Okay, see what is going to happen. Okay, if the bus is at rest, driver is at rest, everybody is at rest. No, all of them have inertia of what? All of them are saying we don't want to move. Okay, now see, okay, this is lady's feet attached to the floor of the bus. Okay, now see, the driver is also very nice. Okay, he's going to put accelerator now, very hard. Okay, he's going to push the accelerator. The moment the driver is going to put accelerator, he's going to really apply force to the bus or not to make it move, right? What is the first thing that's going to move? The bus or the tires? It's not that the bus will go and the bus goes forward because of the tires, right? The first thing that's going to move is what? Tires. The first thing is going to move is the tires. Okay, fine. Agree with this? But the tires and bus body is attached, right? So the next thing going to move is what? The body of the bus. Okay. Then there's chairs. Chairs will move. Chairs are attached, right? This lady's feet also are right now on the floor or not? Her head still wants to remain at what? Rest, but feet are going to go front because the entire bus is going front or not. So it will look like the lady has to fall behind like this or not. I think you can understand what I'm trying to say. Yes or no? Because her head has inertia of what? Rest attached to her body. Okay, everybody's head is attached to the body, of course. Okay, but you got the idea, right? So you tell me, when a bus driver, right, or the bus suddenly accelerates forward, right, where will you tend to fall? Forward or behind? Behind. You fall behind. Okay, and this is because of inertia of what? Inertia of motion or rest? Rest, because her head was at rest, her body was at rest, but her feet are going to go front, no, with the bus. Okay, you got the idea. Okay, okay. And anything else? any more example? Yes, yes.
In place of a lady can take a ball also.
Yes, you could come and keep a ball. If you take a ball and then accelerate suddenly, no, the ball is going to go behind. Okay, okay. Take a skateboard, go home. Okay, take a skateboard. You have, if you don't have, take from your neighbors. Okay. Put a ball here. Okay. Or put a baby if you have at home. Put a baby, and then you push the skateboard. The baby has to fall back. You try with your own or neighbors one. Just bring them for some time. Okay, okay.
When the bus will come back to rest and why we fall in front.
Yeah. We are going to discuss that also. We're going to do that. Okay, but first rest. Okay, I'll show you another example. Okay, see, when you are asked to dust the carpet. Okay, carpet, carpet has dust and all. No, let me draw a carpet. See, you hang the carpet. This is your carpet. You hang it, and you come and beat the carpet with a stick or not. Okay, all these are what particles? Dust particles. What is the carpet saying? I am at rest. I want to remain at rest. Even the dust particles saying I am at rest. I want to remain at rest. When you beat the carpet, right? The carpet will be the first thing to go behind or not. The dust particles will be still there. They don't want to go back, right? So as a result of gravity, the carpet goes behind, but the dust particles are going to fall down. This is how you dust the particles, right? So again, because of inertia of motion or inertia of rest. Because they were at rest, now they want to remain at rest. Gravity will pull it down, no problem with that. Okay, I think you got this idea also, right? Any more examples you can think of? Yeah, I can give you another example. See, tree. Okay, what tree is this? Mango tree. Okay, mango. Okay, so you want to what? You want to, these are branches, okay, which are attached to the mango, no? So you want to get that mango, okay? So what will you do? Start shaking the tree, no? Apply force on the tree. Right now the mango is at what? It wants to remain at rest. Okay, when you push, the branches will be disturbed or not? The branches are going to be disturbed. It still wants to remain at rest. Imagine, okay, the mango is at rest and the branches are moving first or not? So they will apply force in the, what do they have there? What is that called? I don't know. Biology, what is the word? Connection. Let me just say connection, okay? They have connection, okay? The branch and this mango, they will apply force here or not? Yes or no? That force, the mango will stay like this, but the branch are moving or not? So that is going to dislodge, or what do we say? Okay, the mango is going to, I think you got the point, right? So again, this is because of what? Inertia of rest. Okay, some students, I don't know, where are they? Where is Lalpek? Okay, done. Okay, let's go to inertia of motion. Okay, inertia of motion, tell me, what is inertia of motion? A body in motion will try to continue to be in, it doesn't want to stop. Every body has this tendency. Okay, if I throw this also, it wants to go really straight. It doesn't want to what? Stop. Okay, so look at this example. Okay, let's go to that hour. What is that? Bus only. Okay, okay, this is bus. Same lady. Okay, same driver, same lady. She's already fallen back, huh? Before her, just to remind you. Okay, now tell me, this driver also now. Okay, he is a very good driver. He's going to stop the bus, and he stops. He wants to stop the bus right there and there. Okay, so he has to apply brakes or lots of force on the brake. Okay, the first thing to stop will be what? See, all of are in motion, huh, right now. So what does the bus says? I am in motion. I want to remain in, remain my motion, right? Even the lady is in motion. Everything is in motion. Even the tires are in what? The moment he applies the brakes, right, the first thing to stop will be what? The tires. Okay, automatically the body of the bus will also stop, the frame, right? Then her feet, right, will be the first to stop or not? Her head this time will be the last object to stop. Can you understand? Yes or no? So she is going to fall forward or behind? Forward like that. Okay, so what is your question? How will they ask you? Okay, in a moving bus, if there's a passenger standing, right? And suppose the driver puts a brake, right? Why do the passengers fall forward? Okay, and it is because of that, because of inertia of rest or inertia of motion. Inertia of motion. Her head says, her head, okay, saying, okay, I am in motion, I want to remain in what? Motion. I will be the last one to stop here. You can see, because the force reaches her head last. I hope so you got, and still she wants to continue the what? Motion. No, I think you got the point. Okay, this is the example for inertia of what? Inertia of motion. Okay, any more examples can you think of quickly? Inertia of motion. Yes. Again, okay, let's bring a fat one, very fat. Okay, fat. Alok is not fat. Okay, Alok. Okay.
Yeah.
Okay. Think. Who wants to stop or who doesn't want to stop? You did not apply the brakes, okay? The thin one or the fat one? Or both of them, they don't want to stop? Both of them, they have inertia of motion. They don't want to stop. Are you clear? Who doesn't want to stop more? Small m or capital M? Okay, this fat one, okay, doesn't want to stop. Why?
Because of
His mass is more. It's very difficult for us to make this body stop. Okay, imagine now what will happen. The driver puts the brakes. Even this lady falls forward. It's easy for this body to stop or not? Because it has mass or less mass? Less mass means she is trying to resist the change of motion, state of motion, right? But it will be easy for us to stop this body, right? But imagine now this body. It wants to stop or doesn't want to stop? So he can crush the lady, okay? Do you get my point? Okay. Do you understand? It is difficult to stop which body here, lighter body or heavier body? That means heavier body doesn't want to come at rest. So it is inertia or more inertia of motion? More inertia of motion means more difficulty in stopping that body, okay? More inertia of rest means what? More difficult to move that body. Can you understand? Okay, so here also tell me, okay, how do you measure inertia of motion? Tell me. By measuring what? More mass means both more inertia of motion also, inertia of rest also, okay? Okay, we have another example here, okay? See, let's talk about inertia of direction also, okay? See, inertia of direction, huh? If there's a straight road, okay? If there's a straight road, no problem, okay? We are all in the car, okay? This is me, this is you, this is you, this is you, okay? Straight road, no problem, okay? Imagine the car has to take a what? Turn, okay? Very sharp turn, and the driver is, again, same driver. He's going to go really fast and take a turn, okay? When he takes a turn, okay, tell me, what is our tendency, you know? We all want to go in what line? Same line or straight line? All our tendency is to go in which line? Straight. We don't want to change our direction. That is called inertia of what? None of us, we want to change our what? We are moving straight. No, we want to continue moving straight. The moment bus driver changes the direction like this, right? We still want to go where? Straight. That's why when he takes a left turn, we tend to fall towards the right. In a car, it happens. Really happens. You have seen. Okay. Okay, fine. Okay, you got the idea, right? So this is because inertia of what? Direction. Again, if I keep the thin lady and fat boy, okay, what will happen? Who doesn't want to change the direction more? The fat one doesn't want to change the direction more. He's going to fall to the right like anything, okay? Okay. If the windows are and the doors are not locked, he's going to go outside. Okay. One more. I forgot to tell you this very important one. Okay, it has happened to me once. I'll show you what has happened. Okay. I did not know anything at that time. Okay, that's why I see. There's a bus. Okay. Do not try this. Risky.
It's a real life incident.
It happened. I fell down also. Okay. This is the door of the bus. I'm here. Okay. And I was in class 9 or 10. Okay. So I want to get off the bus. The bus has not stopped till now. It did not stop. Okay. So what do I have? Tell me. The bus is still in motion, no? So bus has inertia of motion. Even I have inertia of. I don't want to stop, right? The moment I jump out of bus, okay, and I put my feet on the ground, okay, what will be the first thing to stop? By the way, I still want to move forward, okay, because I have inertia of what? Motion. The moment I put my feet on the floor, my feet will be the first thing to come to rest or not. But my body is still trying to go front. Can you get my point? Yes or no? If my body is still trying to go front, where will I fall? Forward like that, okay? I fell exactly like that, okay? It happened in Rhino. Do you know Rhino? No.
Yes.
Yeah, after civil, you go and you try. Exactly, I cannot forget the spot also, okay? Luckily, okay, just imagine you do that and you get enter somewhere. It's very bad, risky, okay? Don't do, okay? Okay, how to avoid this kind of situation? Not put the hand up. Put the hand up. No. See. You have to do like this. See, when you jump out of the bus, right, you have to keep running to continue your motion. Don't try to just put the floor very hard with your feet. Don't do that. Okay. Try to keep on what running. Then you've seen no this what is that? The conductors are very expert in this. No, you know I think you've seen. Okay. Fine. You got the idea. Okay. Then inertia of direction also we are done. Okay. Now let me tell you what we need to do next. Okay. See. Linear momentum. Okay. See. Very important. What momentum? Linear momentum. You already have some idea. In physics, we define it like this. See. General idea is going to tell you about amount of motion. Amount of motion. Okay. This is the idea behind your what? Linear momentum. We always talk about linear momentum only when there is an object of mass m and moving in a straight line with some velocity called what? V, no? Then we say this body has a momentum, okay? Formula for momentum is what? Take the product of mass and what? Velocity, okay? And this quantity is a vector quantity measured in what? Kg? Meters per second. And this will tell you about the amount of what? Now, if you look from Newton's point of view, no? It's not only about the speed. It is what? It involves speed and mass. Because to change the speed, you have to think about the mass. Can you get my point? Okay, in Newton's laws, right? When we are constructing all the Newton's laws, okay, we always talk about inertia or not. The moment we talk about inertia, right, a concept of what will come into picture? Mass comes into picture. Okay, so motion is not about velocity right now. Velocity can be changed, yes. It can be changed, yes. But depending on what? Mass. If the object is very heavy, you need force or larger force. Larger force to change its velocity or direction, everything. Okay, so motion is not only about what? Velocity from now onwards. Motion is going to include what and what? Mass and velocity, and that's what we do together. We put them together in a single quantity called what? Momentum. Okay, if you go to the right, you have momentum to the right. If you go up, you have momentum up. You go to left, you have momentum to the left. Okay. Linear, I think you can understand. Linear is a word coming from what? Line. Line means straight line. Okay. I told you it's a vector quantity. I told you the unit also. There's another unit for momentum. Do you know Newton's? Second also, I think. Newton seconds or second inverse. We'll check. We'll go to that and we'll check. Okay, don't worry about that. Okay. Now say, you tell me if the body is at rest, what will be the momentum of this body? Does it have motion or no motion? Amount of motion? No, there's no motion, right? So momentum should be equal to what? You can check that because the velocity is 0 right now. So product of mass and velocity will be 0. Okay. A bigger object not moving, still the momentum is what? Okay, so under this case, let it be smaller object, bigger object, or any object, yes or no? If the body is not moving, momentum is 0. Easy idea, okay? You check, okay, still recording, no, I think? Otherwise, last time I was just talking, the voice did not get recorded, okay? Okay, now say. I was saying something more, okay? Yeah, we're talking about momentum, no? If a body is moving, right? Suppose a body of mass m is moving. Let me just calculate one case for you, okay? 1 kg. 1 kg mass moving with a velocity of, let's say, 1 meter per second, okay? Tell me how much is the magnitude of momentum. Multiply. 1 kg into 1 meters per second. This is very simple. 1 kg meters per second. If I really talk about vector in terms of vector, suppose this is positive x-axis, how will I write it? P vector will be equal to 1 kg meter per second square, meter per second I cap. I hope so you understand, right? This is how we are going to write if we are going to write as vectors, okay? So don't worry about vectors right now, okay? Now say, if I start really looking into how the momentum changes, okay, with mass and velocity, let's try this first case. See, momentum is equal to product of mass and velocity, okay? Let me keep the mass constant. And normally, what will happen? Tell me, mass can remain constant or not? You are moving, okay? When you're moving, right, mass will change or not change? No, it will not change, okay? Mass is something which normally remains constant. I'll tell you when does mass changes also, okay? Right now, mass is what? Constant. If mass is constant, joy check, okay? If mass is constant, if the velocity is 0, what is your momentum? 0. I'm going to draw a graph between what and what? Momentum and velocity. This here means 0, yes or no? This means 0 velocity and how much momentum? 0 momentum. Do you agree with me? If the velocity is 0, momentum also? So our graph will start from here. Agree with this, right? Okay. Let's increase the velocity. That means it's moving now, okay? It has some velocity, it has some amount of momentum or not. Let's double the velocity. If I double the velocity, your momentum will look like this. Say, mv or m twice v. So it is the same momentum or it is double the previous momentum? Double. When you double the velocity, the momentum is going to increase. Okay. So if you double the velocity, see, I've doubled the velocity, momentum also will become doubled like this. If I triple the velocity, momentum also becomes what? 3 times. Okay, automatically you'll see this graph is what graph? A straight line, indicating that obviously momentum depends directly or inversely. Directly on v, velocity, right? To the power 1, to the power 1. That's why it is linear equation. What is this? Linear equation, linearly dependent. Linearly dependent always look like this. If I double this, this also becomes double. If I triple this also becomes triple. Okay, you can see it from here. Okay, okay, done. Okay, suppose another object if we want to bring of same mass, I'm repeating again, same mass but more velocity. Okay, I think I don't need to do that. No need. Let's go to the next one. Okay, so sorry. Okay, check. Okay, next case, suppose this happens. Okay, P equals to mv. The previous graph that you saw, right? What did we keep constant? Mass did not change. You were just increasing what? Velocity, and you saw the effect of what? Effect of change of velocity for the momentum, right? Velocity increases, momentum also, but mass should be kept constant. Okay, now see. Okay, let's keep velocity constant. Let's keep what constant? Velocity constant, but let's keep on increasing what? Mass. Let's see what will be the effect. Okay, this is your momentum now versus what now? Momentum will change when you change the mass or not? Check. Yes or no? You want to increase the mass. Okay, that's what we are trying to do right now. Okay, okay, waiting. Zero mass. How much momentum? Zero. Some mass. Some momentum. Double the mass. Double the mass. Momentum also becomes double. Can you understand? So again, you are going to get the graph or straight line. That means this object, right, or any object actually. Okay, if the velocity is constant, then when you increase the mass, is momentum has to what? Increase. Okay, very easy till now. Okay, more mass, it has motion or more motion. If I compare now small object and big object, okay, one of more mass and one of small mass moving equally fast, who has more momentum? Small object or bigger object? Bigger object will be considered to have more motion. Can you understand? Not the smaller object. Okay, you got some idea, right? Okay, now check last one is very nice. Okay, last one is, we try to write this again. P is equal to what? M into v. I have kept the mass constant. I have kept what constant? Velocity constant. This time I'm going to keep what constant? Momentum constant. This momentum also can become constant. Okay, now you are going to tell me how can momentum be constant? Yes, think. Science students, come on, yes. If you are art students, no, I will never ask you any question, never. Okay. Whole year you just come, you can play half an hour song here, dance and go, so no problem. Okay, science student, now tell me the answer. You understand my question? What did I ask you? When is velocity constant? Easy. If the body does not change its speed, no? 10 meter per second, then velocity is constant. Everybody understands that. Mass constant. The object doesn't become fat, doesn't become thin. Moves in the same mass, no? Easy. What is the meaning of momentum constant?
When both the mass and velocity are constant.
No. Let's not go there also. Okay. That is one way is correct. He is correct. Okay. If mass is constant, velocity is constant, momentum has to be what? Good. At least one answer you give correct. That is one option. Another option? Okay, see. Give me any value of mass. Suppose 10 kg. How many kg? 10 kg. Tell, give me any values of velocity. Huh? 28. Okay, give me easy numbers. Wait. 20. Let me take 20. Okay, 20 meters per. Notice something. Okay, now. How much momentum will I get? 200 kg meter per second. That's the momentum right now. Yes or no? Notice if I increase the mass and decrease the what? Velocity, I can still get 200. I'll show you. Okay, I will increase the mass. Let me make the mass how much now? 20 kg into, let me make the velocity 10. Still I'll get equal to 200 or not? Did you notice the momentum is different or same again? So if you want to keep the momentum constant, you can do one more option is there with you. What is that? If you increase the mass, you decrease the velocity, then also momentum can be same. Okay, or the other way around also. You increase the velocity and decrease the what? Then also momentum can be same. Can you get my point? So what did you learn just now? Hey, what did you learn just now? Can we keep the momentum constant or not?
Yes, sir.
How? Increase the mass, but you have to decrease the velocity, or you increase the velocity but decrease the momentum can remain same. Okay, momentum may not change. Okay, okay, you got the idea. Okay, now what graph am I going to draw? Here I already told you I'm going to keep my momentum as what? Constant. If I say momentum is constant, you know what does it mean? That means product of mass into velocity is what? Is constant means what? Product of mass and velocity is constant. If the product of mass and velocity is constant, that means I can write like this. See, mass is inversely proportional to what? Velocity. I think I wrote it too fast. Wait a minute. So mass can be written as what? Or let me say velocity is equal to constant divided by what? Mass. This is indirectly I can say inversely proportional to what? Mass. That is what I was trying to say. See, if you increase the mass, the velocity should decrease. Are you clear? And if you decrease the mass, the velocity should, then only your momentum will be constant. And you can see from the graph, see, suppose this is velocity, this is what graph? Mass graph, okay? How will it look like? Tell me. Is it a linear graph, proportionally linear graph, or inversely proportional graph? Inversely proportional graph. What is the power? 1, what is the power here? Between V and M, huh? Be careful with that, okay? Okay? The graph has to look like this. If you need more explanation, maybe I'll do it later. But for the time being, this is how it should look like. Say, if you keep on increasing the what? Mass, if I go to the right of this graph means what are you increasing? Mass increasing, what should happen to velocity? It's going down, velocity should decrease. Okay, it cannot be this. This is wrong. This is not the graph for this is not the graph for this kind of formulas. Okay, so whenever you see, right, x, okay, let me just show you that very quickly. See, whenever you see a graph like this is y, and what is this? X, and I tell you that y is inversely proportional to what? X. What kind of graph will you get? Curve and goes down like that. Okay, okay. Clear with this? If I write y is proportional to x, what kind of graph you will get? A straight line. Good, very good. Okay, so you got the idea. Okay, no confusion till now. Okay, fine. Okay, now where are we heading to? See, yeah, done. Okay, now we are done with first law actually. Okay, whatever we studied is first law only. I think you can read the statement yourself by now. Done. Okay, second law, Newton's second law of motion. Okay, waiting. Whatever you heard, just say. Whatever you have heard about second, you know second law or what? Momentum. You have heard about momentum. Good. In second law, we bring force. Till now, there was no proper way of defining. Okay, the force is defined now. Okay, okay. You're saying push and pull, right? Newton is going to define like this. Okay, waiting. I thought you guys know, but you don't know. Okay, fine. Force, a rate of change of what? The rate of change of momentum. That means how much is the change of momentum of a body, right? Is directly proportional to how much force you apply on the body. Or by knowing the rate of change of momentum, no, you can know the force acting on the body. Force is something you cannot measure. Say, if I push something, okay, if I push something now, okay, this, okay, I push it. Can you tell me the force? No. I push this wall. Can you tell me the force? No chance. Okay, you cannot tell me the what? Force. How do you measure force? By knowing rate of change of what? Can you measure mass? Yes. Go to vegetable seller also, he can measure mass for you and give it to you if you don't know. Okay, how to measure? Are you clear? Okay, can we measure mass? Yes. Can we measure velocity or not? Yes. Force is measured by measuring those quantities. Because, you check here. What is change of momentum? Let me just show you. Okay, see. This is a body of mass, m. For our cases, okay, I will take the mass to be constant now, okay. Later I'll show you mass may not be constant, but for the time being I'm saying mass is what? Constant, okay. So let's apply force. Before that also, let me tell you, right now it is moving with a velocity, let's say u. I think you're clear what is u, right? U is velocity, initial velocity. Right now this object is moving with initial velocity u, okay? What am I doing? I'm trying to explain to you what is second law of motion, okay? Check. Then you come and apply what? Force. And we know, right? It has inertia of motion. It will not change its velocity unless and until we apply what? Force. Yes or no? So when you apply this force, what will happen? This body will move or move with faster velocity now. Check the direction of applied force. Same as initial velocity, right? So this will increase the velocity to v or not. So now there's a change of velocity, okay? And you will also agree with me that it takes some time for the velocity to change or not. You suddenly cannot reach to that velocity, okay? You are going to apply force for some time And when you apply force for some time or that time, right? The time, okay, is involved or needed to change the what? Change the velocity. Okay, I think you got the point. Okay, now see. See, what is this? V minus u. Please tell me properly. Displacement. V minus u is displacement. Final distance.
Oh, final.
Final velocity minus. What is that? Velocity, change of velocity. What is the initial momentum? Initial momentum is what? Mu. What is the final momentum? Mv. What is Mv minus Mu? Change in momentum, okay, divided by time. What is this called? Rate of change of momentum. And Newton is talking about this. Rate of change of momentum depends directly on what? Applied force. This is applied external force and it is net force. Net. You never take it as single force. It may be single force, but always we look at what? Net force. Maybe 3-4 forces are acting. 3 or 4 forces acting. Which one force will take? Net force, total resultant of all of them. Okay. Ezeric, don't sleep. Okay. Yeah, I know. But you look very sleepy. Okay, don't sleep. Huh? In between. Look bit difficult, huh? Check. Okay. So, do you understand what happened? I'll tell you once nicely. See. If you apply force, tell me, will it still remain to move with same velocity or it will change? So the force is going to change the velocity. Force is going to change the velocity means force is going to change the momentum. Clear, right? But many things can happen, okay? The momentum can change very slowly because time is involved, or the momentum can change very fast. Can you understand? That depends on what? That depends on what? Force. So it is not the change of momentum that depends on force. It is the change of momentum or rate of change of momentum. How fast the momentum is going to change depends on the applied force. Can you understand the difference? One is just simply change of momentum. That doesn't depend on force. How fast the momentum is going to change, how quickly the change in momentum will take place, that depends on what? Imagine you apply 1 Newton. Will the momentum change? Yes or no? Yes. If you apply 10 Newtons, momentum will change 10 times faster. Can you understand? Okay, this is one way to look at this. Okay, I hope so you got the point, right? Okay, so please tell me, okay, what did you learn just now? Rate of change in momentum, right, is directly proportional to what? Force or net applied force? Net applied force. Okay, fine. Implies. Okay, let me remove the proportionality sign. What do you do? Tell me. When you remove the proportionality sign, what do you bring? Equal to sign, no? And when you do that, you have to multiply by what? K. Now this K you can write on the left side, right side, doesn't matter. Okay, it doesn't matter. This K, let me tell you directly, if you follow SI system, is equal to what? Don't worry from where it is coming. No need right now. Okay, waiting. Delta P by delta rate of change of momentum is nothing but a way to calculate what? Because force is something you cannot measure directly, I told you. Yes or no? You calculate the rate of change of momentum. That's how you calculate your force. Okay, now check. Okay, let's write properly. Okay, what is delta P? Delta P is what? Mv minus mu, okay, divide by, let's say this is T only, not a problem, okay, equals to F. And whenever I write like this is the definition of force or average force. What do you think? Final momentum minus initial momentum. If this is instantaneous, no, I will get a time called T or dt. Dt we should get, right, for instantaneous. This is not instantaneous. Instantaneous or average? Average. I'll show you for instantaneous also, okay? Waiting. What is this? Can I take M common here? So I can write here V minus U divided by what? T, and everybody knows what is V minus U divided by T is. A change of velocity by time. A, yes, very good. Okay, equals to 4. That's why what we have proved just now. F equals to ma. That means you can know whether there's a force acting on a body or not. Net force is acting on a body or not, okay? By knowing what? Acceleration of the body and the mass of the body. Can you understand? Okay? If I ask you now, if I draw a graph between what and what? Acceleration and force. Tell me now directly. You will be so smart now to tell me. Acceleration, 0. How much force? Net force will be 0. Some value of acceleration, some value of force. Double the acceleration because power 1. Double the acceleration, force also will become double. Yes, that means to produce twice as much as acceleration, right? You need a force or twice as bigger force. Twice as bigger force. Okay, I think that you can answer. That's why you get what kind of graph? Straight line again. Makes sense, right? But I told you at the beginning also, what will be constant? Mass will be Constant. For the time being, let's not go to a case where mass is not constant. Okay. Now see, clear till here at least. Okay, done. Let's talk about unit of force also directly. Waiting. Kg meter per second square. In short, we call it Newton. This is unit or SI unit? SI unit of force. Okay, fine. Till now, everybody is happy. Okay. Let me show you what can 1 newtons of force do. Okay, see. If I take a body of mass, exactly what? 1 kg, and you produce an acceleration of exactly, let's say, 1 meters per second square. Do you understand the meaning of this? That means this body will move with constant speed or it will increase the speed. Acceleration is there, no? That means speed will increase. The speed will increase to what? Let's say start from 0. 0 meter per 0 meter per second. Then it will become how much? 1 meter 1 meter per second. After how many seconds? Because that's the meaning of 1 meter per second square, no? I think everybody knows this one, right? Let me write here properly. See, acceleration equal to 1 meter per second square means what? After every second, the velocity will change by 1 meter per second, 1 meter per second after every per second, right? So that's why we write per second square, okay, for acceleration, right? Check. So when you start with 0, right, after 1 second, what will be the speed? Acceleration is there of 1, so it will gain the velocity by 1, right? After another 1 second, what will happen? 2 meter per second. After another 1 second, 3 meter per second. So after every 1 second, this body, according to this, right, is going to become faster and faster and faster or not. That means you are constantly applying a what? Force, which is equal to how many newtons? 1 kg into 1 is 1 newtons or not? So tell me, what can 1 newtons of force do? If you take a body of 1 kg and apply a force, right, equal to how many newtons? Or let's say the body of 1 kg has an acceleration of 1 meter per second square. That means every second speed is increasing by how much? There's a body, you see its speed is increasing every second. How much? 1 second, 1 meters per second, another 1 second later, another 1 meter per second, another 1 second later, 1 meter per. So every second's body's speed is increasing. And the body is how much mass? 1 kg. That means you are sure that you applied a force of 1 Newton. Are you clear or not? 1 Newton can do what? Tell me again, guys. 1 Newton is a force which can produce an acceleration of how much? 1 meter per second square in a body of how many kg? If you apply this force of 1 Newton to 2 kg, what will happen? Check, okay? How much force you applied? 1 Newton to a body of how much mass? Tell me, it will have same acceleration or less acceleration? Less acceleration, because from here you can calculate acceleration equal to what? F by m. If there is a bigger mass, what kind of acceleration you will produce in that mass? By the same force, less. I hope you got the point, okay? And why it is happening again? Because of inertia or not? More mass means what? Easy to change the speed or difficult to change the speed? So that's why the acceleration will go down. Okay, a little bit is clear at least? Okay, fine, okay. I hope so till now everybody understands, okay? Second law, okay. Till now we have reached it. But let me just show you the instantaneous force formula also, okay? See, rate of change of momentum. I'll take a break after that, okay? Check. So you know about this, F equals to delta P by delta T, right? Let me bring the limits in time, see. If I write limit as delta T tends to what? 0, then I write and define the same thing, see. Now you tell me, okay? Now, am I talking about change of momentum or sorry. Now am I talking about change of momentum or very quick change of momentum? Very quick change in a very short time, okay? Now, this is what is known as what? dP by what? dt. This is your force or instantaneous force? Instantaneous force. I hope you understand the difference between this, no? Okay. So no problem at all. Till now we are doing fine, okay? I think I'll take a break, okay? Till then, what will you do? No. Break is only for me. You guys, why do you need break? You guys are young. Stop.